I'll take in a very quick example again to make it more graphical, and my graphical means it's all A, B, C, D, E. So I say A and B and C implies D, E, D and F implies G, and E and A and G implies H. Now what I could do is I could make a and or graph for it. So I'll have to add in more terms in order to get the all components as well. So it's D and G implies E, and it's, let's say, D and A also implies G. So E could be inferred by either this or this. That's the or. E has to be inferred from A and B and C. That is what is and. So let's convert it into a graph. So E has to be inferred from, oops. So E has to be inferred from A and B and C. A has to be inferred from A and B and C. G has to be inferred from D and F. This shows it's and. H has to be inferred from E, A, G. So E, A, G, H infer H. So that's E, that's A, and this is G. D and G, they infer E. D and G, they infer D and G, they infer E, and D and A infer G. So D and A, they infer G. D and A, they infer G. Okay, so now let's try to see what happens. So E can be inferred either by this or this, and this itself has all the three, and this itself has all the two. If you're following the book, you won't see really these nodes separate. You could see something like this, which is a short form of exactly the same thing up. It's just that this is a little bit more clearer usually to me. So now let's do a forward pruning, and in order to do a forward pruning, let me say that D was true, initially known to be true. F was also initially known to be true. For everything else, I absolutely do not know. Now, D is true, F is true. DF, 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 DF. So I imply G is true. So DFG is known to be true. DFG is known to be true. So this is the only rule that I can apply. D is true, G is true. That means E is true. And my query was, say, on H. H is EAG. A and G. Okay, I forgot to add A is equal to true. So H turns out to be a true. Forward chaining. If you want to visualize, you can visualize about how these nodes will be ground and or search, how these nodes will be ground to a true, which is blue, which is positive, or false, which is negative, or black. So if you want to visualize that up, I could do that as well. So initially these were supposed to be true, EDF. So ADF, so you color A, you color D, and you color F to be true and do a normal and or search. Now, the and or search could be done in two parts. The first is how I did. So I looked into the rules which could be true, I applied them, and I propagated this red color in this graph. I searched for rules which could be true. This is what's called as the forward chaining or the data-driven approach. I look at the data and I try to extract more and more knowledge, more and more facts. On the other hand, since this is an and or graph and we've already discussed and or graph, of course it will come in your mind that because this is an and or graph, I could apply a depth first search in this and or graph, and the moment I apply a depth first search in this and or graph, it becomes a new algorithm called as a backward chaining. And I need not teach that to you because we already had the discussion on and or graph. That time it was for a tree because the states were infinite. Now the states are finite. You can take closed, you can take transposition, you can take memory, you can take visited, you can take whatever name you have for these concepts. So quickly going on to the same thing. For H, I need to prove A to be true, which is true. So I just return, it's already known to be true. E needs to be true, depth first search. That means B and C need to be true. And because B and C need to be true, okay, I may have made in a bit. Okay, yeah. So I go in the depth first search, A, I return back immediately. I go to E. E needs to be true. For E, either this branch needs to be true or this branch needs to be true. I go here, B is false. Now in AND, if one of them is not satisfied, there is no way to satisfy that up. There's no need to try the other branch. Otherwise, you could go to C, it will also be false. AND or true, false, false will be false. Then it's a DFS. So I go around over here. So D is true. Wonderful. G, I try to satisfy G, it's a DFS. I go to A, which is a true. I go to D, which is a true. That means this becomes true, DFS. And because G becomes true, then I return to my node. So it gets true from this branch, it gets true from this branch. That means it gets true. I go back to H, I go to G. It's already true, so I just return a true in my DFS, and this is turns out to be true. So backward search, backward chaining, I need not explain anything. You already know backtracking. The only difference is this time there is no memory problem. The complexity is linear. Store in whatever goddamn thing you need to store. This is also given called as a goal-driven approach. So I just note down the differences one by one. We discussed forward chaining first. And we discussed backward chaining. Here I look at the antecedents and I try to make as many consequences as true as much as possible. So that's data driven. I see how all can I make it true. The moment I made goal as true or my query as true, I just break, and this is what is goal driven. I look at what goal I need to make it true, and then I say, okay, how will I make this true by either this or this? Okay, how will I make that true? And I go in a backtracking DFS manner. And it so turns out that normally, at least till now, you will prefer backward chaining as goal driven, considering that there could be a lot of irrelevant facts. And goal driven, you select the necessary facts and your chances are, so that's a heuristic that you get through earlier. In terms of strict complexity, there is no such thing. The complexity will turn out to be exactly the same. You're just doing an exhaustive search. With that, I also come into the same thing that I said with every approach, and that's why when I was dealing with constraint satisfaction problem, I said this is the deep learning of classic AI. Be very careful. Forward chaining. Would I like to use interesting heuristics? This rule is more important than that. Yes. Backward chaining. Would I like to say that given I can visit all these branches in any order possible, I should prefer this over this or this over this? Can I generate interesting permutation combinations of the branches so that in case of and, if it fails, that one is to be tried first so that everything else is pruned out? In case of or, my probability of success is more. Same constraint satisfaction problem. Just look at it as a constraint graph. So everything turns out to be the same old heuristics, although we may not have really worked around on those heuristics in any case possible. And with that, I finally conclude the lecture. Thank you.